So first, let's do a quick review of exponentials and logarithmic functions. Y is equal to 10 to the x, so if y is equal to 10 cubed, then y must be 1,000. If y is equal to the common log of x, for example, y is equal to the common log of 1,000, then we're looking for the exponent of 10 that's necessary to produce 1,000. That exponent would be 3, therefore the common log of 1,000 is 3. Notice that what we just got was a situation logarithmic function where we entered 1,000 for x and we got back 3 for y. But in the original exponential function, we put 3 in for x and we got back 1,000 for y. These are inverse functions because they switch the x and the y. If we look at y is equal to the common log of 100, then we're looking for the exponent of 10 necessary to produce 100. That common log must be 2. Now we can go back to this basic function y equals the common log of x, and we can think about raising both sides as a power of 10. Well, now what we're looking at on the right side is the common log of x is the very exponent that goes with 10 to give you x. So whatever that very exponent would be, you know it's going with the 10 to give you x. Therefore, 10 to the common log of x is just giving you x. Going back to the left side, similar thing happens. We have 10 to the y, but remember initially y was equal to log of x, so we can replace y with the common log of x, and by golly, the same thing happens. So we get x equals x. What we are witnessing is the ability to use inverse functions to undo the original function and produce a linear relationship.
So if y equals the common log of x, we can get x by itself and undo the log function by raising both sides as a power of 10.
Logarithms are exponents, and therefore they behave like exponents. 10 squared times 10 to the third is 10 to the 2 plus 3, or 10 to the fifth. Now 10 squared cubed is equivalent to 10 to the 2 times 3, or more importantly to us, 10 to the 3 times 2, which is 10 to the sixth, or a million. So we go back to this function, y is equal to the common log of 100 raised to the third, and now if we raise both sides as a power of 10, here's what happens. We get 10 to the y is equal to 10 raised to the common log of 100, all of that cubed, but the common log of 100 is 2, so we are at 10 squared raised to the third, which can be written as 10 to the 3 times 2. So we get 10 to the y is equal to 10 to the 3 times 2, but now let's undo this process. We can replace 2 with the equivalent common log of 100, and look what we get. We now see that both exponents must be equivalent, and therefore y is equal to 3 times the common log of 100. So this is important to us. All we have to do when we see something like common log of 100 raised to the 3 is we know that we can put the 3 in front and multiply it by the log of 100, because the log of 100 is an exponent and 3 was an exponent, and logarithms behave like exponents. Try this one. Y is equal to the common log of 1,000 raised to the second power. We know that we can put that second power in front of the common log and make it look like this, so we get that y ultimately is equal to 6. Logarithms have been important to us in the past. Here's a very simple equation that we can solve. When we try to solve an exponential equation, meaning the variable is in the exponent, we have the right to use a logarithm on both sides to solve. In this case, we would use log base 2 of both sides. The x is that exponent that can come in front. Now we have a linear situation. We can just divide by log base 2 of 2, which is a constant, which is really equal to 1. So in the end, we're left with x is equal to 5 divided by 1, or just 5. At any rate, this basis of understanding logarithms and exponents a little bit will help us now as we move into transformations to achieve linearity.